All right, in this section we're going to be starting a discussion on power series and the ratio test. So in this section, what we do is we're going to be moving from polynomials with finite many terms to power series, which are polynomial-like functions that have infinitely many terms. And so this word series right here, that is what indicates that we have infinitely many terms. In terms of modeling functions, this is the leap from Taylor polynomials, which are only approximate representations for a function, because the Taylor polynomial has a finite number of terms, to a Taylor series. Again, here's this word series, which is a way of representing functions exactly because the Taylor series does not stop at a certain number of terms, but goes to an infinite number of terms, which will model functions exactly. The Taylor series is more than an approximation for the function. The Taylor series is actually the function. For example, the Taylor series for sine of x or cosine of x, those actually are the actual value of sine of x and cosine of x. All right, so let's consider the function f of x is equal to square root of x, centered at x equals 4. The graph here suggests that there's a convergence issue. It appears that the series converges from x equals 0 to about x equals 8, because that is where the Taylor polynomials appear to fit the function well. All right, so if we look at this graph right here, the black graph is the function square root of x, and then we have the red line right here. That is our first degree Taylor polynomial, which is simply a tangent line, and it is tangent to square root of x at the center, which is 4 right here. So this value right here, that is going to be the center. And so remember, from your Taylor polynomials, the further you get away from that center, either going this direction or this direction, the further you get away from that center, the less accurate your approximations are going to be. Now, when we were doing the Taylor polynomials, for example with sine of x, as we increased the number of terms, that polynomial became more and more accurate, or in other words, it modeled the graph of sine of x better and better and better. And so we said that as we went to infinity, it would continue modeling that function out to infinity. Square root of x, we've got a different issue here though. The square root of x, these are different Taylor polynomials. The red one here is a first degree Taylor polynomial. This one is a fifth degree Taylor polynomial. The one over here, the purple one, this is a 10th degree Taylor polynomial. And we've got a 15th degree and even a 30th degree Taylor polynomial. Now, as you notice, what happens is right around this vicinity here, our Taylor polynomials start to deviate from the square root of x. And even though we are increasing the number of terms out to even 30 terms, it is still deviating away from that function. What that means is that the Taylor polynomial will converge here, which is between 0 and 8. So we've got a convergence to the function square root of x. But after 8, your Taylor polynomials, are going to start deviating away from square root of x. And even though we increase the number of terms by a lot, it is still not going to get close to the square root of x. It's going to deviate from it. That means it diverges after x equals 8. Between 0 and 8, this function converges, but to the left of 0 and to the right of 8, it diverges. Okay? Now, the center right here, that is going to, well, from here to here, this is going to have a term for it. This is called the interval of convergence. And so our interval of convergence would be from 0 to 8. Now, at 0 and at 8, we're not sure yet whether it converges or diverges at those particular numbers, but we do know in between them that it converges because it models that function very well. Okay. Now, the distance between the center and the 8, that distance is going to be called the radius of convergence. Between 0 and 8, that's the interval of convergence. And from the center to one endpoint, that is going to be your radius of convergence. So the radius of convergence here is 4. Okay. All right, so the idea of convergence and divergence of power series will dominate the remaining unit that we have on series. We're also going to look at determining what the radius of convergence is, or in other words, what is the interval over which the series converges to the function in question. So let's answer this first question. What is a power series? All right, so a power series is centered at x equals a. It is an infinite series in this form. All right, so we have a sum going from n equals 0 to infinity, and it doesn't really have to start at 0. It could start at 1 or whatever, but it does have to go to infinity in order to be a series. C sub n just simply represents whatever the coefficient is for our terms. And this coefficient can take on a lot of different forms. Just know that this is a coefficient that is dependent on the value of n. All right, and then that coefficient is going to be multiplied by x minus a, where a is going to be the center of our series, and then raised to the n power, which means the exponent here is going to be increasing as we increase the number of terms. This a value has to be the same value in every term in your series. So if it is a Maclaurin polynomial, a would be 0. And as we have seen before, every power series will converge at the center. All right, so a power series may converge for some powers of x, but not for others. The set of x values for which the power series converges is called the interval of convergence. And so we looked at that on the other slide with the square root of x graph. And the center of the series is always in the middle of that interval. And so in the case that we were looking at, 4 was the center. The distance from the center of this interval to either endpoint is called the radius of convergence. And that is an absolute value because it's going to be a distance. And this is often denoted as r. There are only 3 scenarios that we can have with this situation. The first scenario, and this is the worst case scenario possible for convergence, and that is if r is equal to 0. This means that your radius of convergence is 0. Well, what that means is that your polynomial is going to diverge everywhere except for the center, because all of them converge at the center. All right. The best case scenario is if your radius of convergence equals infinity. This means that the series converges everywhere, which is what happens with your sine function. It converges everywhere. Same with e to the x, cosine of x. These are ones we've looked at already. These are going to converge everywhere when we refer to this as a series. And then the other function, or the other scenario, if r does not equal 0 and r does not equal infinity, then what we're going to be looking at then is r is going to be greater than 0, and it is going to be a finite number. For example, r might be 5 or 6 or 2. In this case, the series converges when the absolute value of x minus a is less than r, and it diverges when the absolute value of x minus a is greater than your radius of convergence. Okay. All right, we'll also need to discuss whether the series converges or diverges at the endpoints, and we'll do that a little bit later in the chapter. This will also affect our interval. For the square root graph on the other page, the center was 4, and the radius of convergence was also 4. This means that the interval of convergence could have been 0 to 8, which means it converges everywhere between 0 and 8, but not at 0 or 8. The interval of convergence could be like this. This means that it diverges at 0 and converges at 8. This means that it converges in between 0 and 8, and at 0 it converges, and at 8 it also converges. And this one means that it converges between 0 and 8, and at 0 it converges, and at 8 it diverges. It's just like your interval notation that we used for domain and range. When you had parentheses, that meant the number was not included. Bracket means the number is included. So when we're talking about interval of convergence, the bracket means that this number is included in the convergence. Parenthesis means this number is not included in the convergence, which means at this number it diverges. All right, so we're going to look at this first example here. The power series given by this converges for x equals 3 and diverges for x equals -5. For each of the following x values, state whether the series converges, diverges, or if the convergence at that point cannot be determined. All right, so what I'm going to do here is think about this on a number line. All right, so we said that this is so if we look at this right here, what this tells us is that the polynomial is a Maclaurin. It's centered at a is equal to 0, and so I'm going to think about this in terms of this number line right here, and I'm just going to mark this off, 0 being the center, and we know that it always converges at the center. We're going to have 1, 2, 3, 4, 5, 6 this way, 1, 2, 3, 4, 5, -6 this way. I'll mark off a few points here. All right, so let's indicate what is happening on this. The problem says that this converges when x is 3. All right, so it's converging right here, and diverges when x is -5. So we're diverging over here at -5. All right, so what's happening at all of the other points? Well, what we want to look at then is what's happening from here to here. If this converges at 3, then that means our radius of convergence is at least 3. All right, so that means everything between here and the center has to converge. All right, so I'm just going to mark C on these. And that also means that everything on the other side would also converge for that same radius. Now, the radius is going to be at least 3. Now, we know because we were told at x equals 3, it converges. However, at the other endpoint, which would be a -3, we do not know if it converges or diverges at the endpoint. We do know that everything in between will have to converge. So we'll have to converge at -1 and at -2. I'm going to put an I at -3, saying we need more information to determine if it is converging or diverging. All right. And so now we want to look at some of these other points here. We knew it converged here, but we do not know if it converges here at 4. We also do not know if it converges or diverges at -4. We were not told that 3 was the radius of convergence. We were just told that it does converge at 3, which means that could be the radius of convergence. The radius of convergence could also have been 4, but we do not know. Therefore, we do not have enough information to say whether it converges or diverges at 4 or at -4. Now, we do have this information saying that it diverges at -5. All right, so what if our radius was 5 for our radius of convergence? Well, -5, it is diverging, which means +5 would be the other endpoint. We do not have enough information to know whether it converges or diverges at 5. Now, since it does diverge at -5, that is at most what our radius could be, from 0 to 5, -5 and +5. That's at most what the radius of convergence is, which means everything outside of that has to diverge. So at -6 and at +6, it must diverge. All right, let's look at one more example here. On this particular problem, says the power series given by this converges at 6 and diverges at x equals 8. And we're trying to figure out what's happening at all these other different points. All right, so like I did before, let me just draw a number line here real quick. Now in this particular problem, we have x minus 2, which means 2 is our center of convergence. So I'm going to use 2 on my number line right here. That is our center, which means we know it has to converge at that particular value. All right, so we're going to have 3, 4, 5, 6, 7, 8, and then 9 on this end. I'm going to go -1, -2. I'm sorry, wrong value. 1, 0. -1, -2, -3, -4, -5, -6, -7, and -8. All right, so with this, let's go ahead and mark on here what we know. And we know that it converges at x equals 6. And so we're going to go ahead and mark this. I'm going to leave the other piece of information alone for just a minute. And let's talk about this. Now, we know this is the center. And so what happens if our radius of convergence is 4 right here? And let's say this is our endpoint. If this is our endpoint, then everything in between here and here has to converge. So we've got convergence here, here, and here. And if we go 4 units the other direction, that would put us at -2. Now, -2 would be the other endpoint of our radius of convergence. And at the endpoint, it does not necessarily have to do what the other endpoint does. And so we don't have enough information to know if it converges or diverges at this point. But we can say everything up to that does converge. Okay? And we don't have enough information for that value. All right, so we also know that this diverges at 8. Well, now what we want to do is think about this. What if this was our other endpoint? Well, it could have been the other endpoint, in which case 7 would converge. But since it does not converge at this, we don't know if this is an endpoint. This is not necessarily included within that interval of convergence. It could be an endpoint, it may not be. We don't have enough information. And so we don't have enough information to say if it converges or diverges at 7. Now, the radius from 2 to 8, that radius is 6. So if we go 6 units in this direction, we do not know if it converges or diverges here or at -4. We do not have enough information for these two values. Now, it does diverge at 8, which means everything after that has to also diverge. So it has to diverge at 9. Now, the radius here from 2 to 8, that's 6, which means everything after that would have to diverge. So if we go 6 in the other direction, everything after -4 would also have to diverge. So -5, -6, -7, and -8 would all have to diverge. All right, so the next problem, what we're going to be looking at doing is going to be finding the radius of convergence of this power series. Now, in this particular power series, when you have some number raised to the n power, that's going to be a geometric series. And this will converge if the absolute value of this is less than 1. Now, if you multiply your 2 to the other side, that is going to give you absolute value of x minus 3 is less than 2. Now, this fits the format of what we had on the other page, which said x minus a is less than r. And so what this means is 3 was the center of our polynomial or series, and then this means that our radius of convergence has to come out to be 2. So in this case, the radius of convergence is 2. All right, so if this series is centered at 3, that means 3 to the right and 3 to the left. 2 units to the right of 3 and 2 units to the left of 3. That would give us our interval of convergence. So our interval is going to go from 1 to 5. Now, 1 and 5 are the endpoints of this interval. And so we do not know what's happening at the endpoints yet. Like I said, we'll cover that later in the chapter. But we do know everything in between here does converge if our center is 3 and our radius is 2. Now, let's look at g of x for a second. This series is derived from this. This is simply the derivative of this one. You bring your n to the front and then subtract 1 from it, and you're going to end up with this series right here. Since this series is the derivative of this one, this will also have the same radius of convergence.